to chapter 2 on the Poisson processes.
Recording in progress.
So let me start off with the section 2.1 on the exponential framework and review on exponential distribution. Probably you guys have been familiar with that, but just let me recall. A random variable x is being is set to have an exponential distribution denoted by x distributed as an exp lambda, where lambda is a positive parameter. If the density, right, so the PDF density function is given by lambda e to the negative x on the domain. I'm sure you have seen this. Let me mention the first elementary fact concerning exponential distribution. Fact number 1 is fact 1A is the so-called memoryless probability. Namely, the probability that x greater than t plus s conditioned on x greater than t is the same as the probability that x is greater than with the difference which is s. Alright. Pretty, I would say not really difficult to prove it. Not really difficult. So let me skip that and mention to fact. So that is fact 1A. Then let me mention the next one. B. So suppose to have an x1 being distributed as exponential lambda 1 up to x n exponential lambda. Right. Then denoted by v to be the minimum of that x1. So we should say they are independent. So R to say are independent, right? Then V is distributed as. Someone still remembers that? Minimum of the collection of independent exponentials. Then the minimum
Still exponential?
is an exponential, but with what parameter? What is the parameter for the exponential?
Is the sum divided by 2?
It's actually the sum. So the sum of the parameters. So the minimum is exponential. With the parameters being lambda 1 plus up to that. Right. So, that is fact, 1B, so now let me mention the last one. 1C. So denotes by, I in the index of the minimum. So let's say this is, let's say, this might to be K, where, xk is the minimum of, x1, xn. Alright. Then, here is a random variable taking value in, the collection 1, 2, up to n, and probability of I, B, and K, alright, is actually lambda K over the summation of lambda. Alright. So let me write up the following, so exponential lambda, and then have, so the density given by the CDF, probability of x less than t is 1 minus e minus t. And what's the probability that x greater than t is e minus t? Okay. And then suppose I have x1 as an exponential what? Exponential number 1 independent. So to next n exponential number n are independent. Then the minimum of these guys has an exponential summation number. Alright. Okay, so then suppose I have xi be a view d exponential lambda, then the sum of them as we go to n is what? A gamma. So the sum of exponential, a collection of IID exponential is a gamma. With the two parameters, alpha, b, and n, and the beta be the summation of, be exactly 9. Therefore, PDF is given by, so f of the sum of the little x is lambda to the n, x, and the alpha, so n minus 1, e minus lambda x over gamma n. Note that gamma n is actually n minus 1 order. Alright. Let's just say it's positive. Alright. Okay. So in the left board book there is the basic facts about exponential. And here, I'm talking about here, the minimum.
Will this be on weekend?
I'm sorry?
Will this be on weekend? Will this,
Who is this one? Sorry?
will the chapter 2 be on the weekend?
No, only covers that one. Okay. So how do I prove that? Let me just walk through this pretty quickly. I'm sure you guys can work it out on your own. So maybe of C only. Okay. Shouldn't be too difficult here. And what I'm going to do is I'm gonna start with two only. So I guess I'll say step one. Consider and B two. Okay. So I'm gonna prove this relation here. So this relation star for n being 2. And then I'm going to generalize up to for any generic n. So here I want to show what I want to show. So I want to show the probability the index of the minimum being 1 is lambda 1 over lambda 1 plus lambda 2. Alright. So this is pretty much your calculus. So what is this? So the probability, the minimum, index of the minimum is 1. That means I would need to have x1 is less than x2. x1 less than x2. And well, so this is just a double integral. I have a well, I guess I want to sketch it out just to make sure. So in this plane, x1 is less than x2. So it's up to you whether you want to go with which one first. Let's say I want to go with the x1 being bounded above x2. So this is the line I'm looking at. So this is the line x1 being x2. So this guy is smaller than this. So I'm looking at this area. Right? And that integral will be the double integral. So x2 will be running freely. So if you run to infinity of dx2 and the density of the x2, so f of f2 x2, right? And then for each x2, is that correct though? Am I correct? Well, if I want to go with the x2 first, that means I have to fix x2, sorry. So it shouldn't be this direction. So if I fix x2, x1 will be running in this line. Right? So x1 being 0 to x2, f1 is dx1. Yeah. Across here, the fi's are the density of the x1, x2, and because they're independent, so the joint density is just the product of the densities. Okay. What is the integral of the first guy? So this inner integral is simply the CDF of x1. This is so this right here is the probability the random variable x1 is less than the middle x2. And so according to the formula above there, that is 1 minus e minus lambda 1 x2. And then I have dx2. Okay, so now I'm going to plug in this. This is lambda 2, e minus lambda 2 x2. first one is simply one, because that is the total integral density. So this is one. The second one, in order to simplify it, that would be lambda 2 over lambda 1 plus lambda 2. Yeah. I guess I'm going to go like this. Lambda 1 plus lambda 2. E minus lambda 1 plus lambda 2 minus 2. Minus 2. Yeah. Of course, that is how you would want to simplify the integral. So this is equal to 1 as well. And the final answer will be, well, 1 minus lambda 2 over lambda 1 plus lambda 2, giving way exactly lambda 1 over lambda 1 plus lambda 2. Which finishing step number 1 on two exponentials. Just count this. So now let me move on to for any generic hand. Step 2. Consider say, and start 3, say, okay. Then I have what? So probability, as usual, so I'm using the 1, right? The index of the minimum is 1, that means probability of x1 being the minimum of the time, and this is the same as the probability of x1 is less than the minimum start of x2. So this is the same. Right? If x1 is the minimum of the whole collection, that is the same as x1 is less than the minimum counting starting from 2. And well, so this is exponential lambda 1. This is exponential lambda 2 plus that plus lambda. Right? According to the factable there, the minimum of a collection of exponential, this exponential. So in view of the computation from step number 1 here, this is exactly the lambda 1 over the lambda 1 plus this. So lambda 1 plus lambda 1 plus summation of the lambda k starting from 2 to n. In other words, this is lambda 1 over the summation of the k starting from 1 n. Yeah, this is step 1. Step 1 calculation. Okay. Yeah. Of course, over here I need to include the fact that they are independent. So otherwise that wouldn't work. I need them to be independent for sure. Okay, so that is right. And that is the fact 1C. Let me move to the last piece in this short section. they're under the same hypothesis. Okay, so xk exponential and k are independent. Alright. Denote again by v being the minimum of them. And the first located in one. And I'm reading k is that as can be the minimum of xi. And then the conclusion is v and I are independent. So the index of the minimum and the minimum itself are independent. Anyone here took 178? No? Yeah? Seen that, right? No? No? Oh, okay. So, it looks a little bit mysterious, but actually the proof is not that difficult. It's just based on, again, based on calculus. So, how do I go? This is one good. I need to show what the probability of, let's say, being equal to 1. Of course, the same would work for any case, so let's just take 1 for the sake of notation. B greater than t. This is supposed to be equal to the product of this probability and alpha. Right? So that's what I want to show. And so let's start from here. I have the index of the minimum being 1 and b greater than t. So this is equal to probability of x1, right? Being the minimum for everyone. Okay. And x1 is supposed to be greater than t. So now we need to have a collection of integrals. Okay, let's go further. So what does that mean? So that is the same as x1 greater than t. And so I have x2 greater than x1. Up to xn greater than x1. Right? So now you're going to have a, let's say, pretty much you have n integrals. I'm going to start from this guy over here, x1 greater than t. So that means I need to integrate starting from t up to infinity of dx1. And I need to plug in the density. So f1 is 1. Right? And then for each of this little x1, x2 is supposed to be greater than that. So x2 is running from 0 x1 up to infinity. f2 x2. So I have the x2 out. Similarly, keep going forward. So x3 is the same, x3, so this is x3 greater than x1. So I would have x1 here to infinity, f3 is 3, here is 3. So you keep going. This will be x1 to infinity, fn, here is it. Yeah. I mean, it shouldn't be too bad here, even though you have like n integrals. But once we are rearranging the integral with the dx, then we good to go. So this is what I have to rewrite this to infinity, f1 and so on. And we have this one. So then we're gonna group the xk with the xk. So x1, f2, x2, dx2, x1, f3, x3, dx3. All the way to x1 to infinity of the density n xnd z. And now, again, this is the probability of the big x2 greater than the little x1. And this is equal to e to the minus lambda 2 x1. And well, similarly for the other guys, this goes down to t infinity. So if you just plug in the formula of the density, so f1 is going to be equal to lambda 1 e minus lambda 1 x1 times e minus lambda 2 x1 e minus lambda 3 x1 e minus lambda x1. Actually x1 here and the x1. Combining everything, I have lambda 1 going outside, t infinity, e minus lambda k times x1 and x1. And well, in order to simplify this, pretty much this is like exactly. So I have lambda 1 over summation of lambda k times t to infinity, summation of the lambda k, e to the minus summation lambda k of x1 dx1. So that's what we recognize this. It is the probability of the minimum greater than t. And the other one is just the probability of the minimum min-axis one. So pretty much this here is the probability I being 1. So that will give me the independence. Calling because V is exponential with this some blank K in my parameter for B, and this was from the previous fact, right? Yeah. Question? It shouldn't be difficult. It shouldn't be. It's just a matter of, the only difficulty is just to convert the probability to the integral. The rest is just calculus. So, eventually you get, after all, shouldn't be that, too much abstract. Alright, so, that should be it for the review on exponential. And then we move on to the 2 on Excel processes. Right. Let me give a motivating example. A motivating example. Suppose I have a modeling of arriving guest starting from time 0. Right. Suppose I have the first guest arriving at this time, let me call it T1. So first guest arriving. Okay. And suppose independent of that, after the first guest arriving, I have at the time T2, second guest arriving at the time T2. So this, okay, so for the second application, I will call this to be a tau 1, and this is a tau 2. Right. So the modeling says the tau 1 and tau 2, they are independent. Okay? So we want to modeling of the arrivals of guests, alright, where we assume the following. Well, we assume tau 1, tau 2. So I guess I want to have like a T3 over here. This is my tau 3. Tau 3 are independent. Okay. And what else can I assume on this? That's a very basic model. I assume the arrival time are independent, and then I assume, well, the simplest continuous random variable taking a positive value is an exponential. So assume further tau k or distributed as an exponential lambda. Okay. And then I have a model for the number of the guests arriving at, say, a restaurant or a bank, for instance. And so I am interested in, the question that I am interested in is, so under that simple model, the question I'm interested in, the given the time t, given time, time s, alright? I want to know the distribution of number of guests arriving before time s. Okay. That is a question that I would be interested in, given this simple model. You can think about it. Right? This is the time 0. This is a fixed time s to the future. And so each time I have a guest arriving here, so t is of k, and then I have t is of k plus 1. The inter-arrival time, this is time 1, this is time 2, this is time k, and this is time k plus 1. Alright. So here, in this particular example, okay, in this particular example, so let's say in the above, we see that number of guests before time s is the relative, which is random, right? Which is a random value. And how do I gonna find out that distribution? So k is a random variable for sure. I want to know the distribution of k. Yeah. All right. And that number of guests arriving before time s, that unknown number is so-called a Poisson process. It's a so-called Poisson process. Well, the reason why it's called a Poisson will come in a moment. But first, just let me give the definition. So, definition number 1. Suppose I have a sequence of tau k being e distributed as an exponential lambda. Right? Let me denote t sub n, capital T sub n, to be the summation of tau k, k from 1 to n. This could be thought as arrival time of the n guest. And let me denote for a fixed s and sub s being, that will be the maximum of n, such that Tn is less than s. Right? Then n sub s is called a Poisson process with the rate lambda. Okay. For instance, here in that picture again, here, let's say I have 0 first guest, second guest, third one, and fourth one arriving after s. So in this particular example, ns is equal to 3. For instance, the maximum of n, just that Tn is less than this. Alright? Okay. So, why the name Poisson? That's because actually the distribution of the nth of s under that assumption on the tau k, it is actually a Poisson distribution. That is the definition one. I'll say this one. Second two now. Yes. So now definition one, so now one, two. So the truth is ns is a Poisson with the rate ns. Okay. So why is that the case? Well, just need to evaluate. So proof here. I want to show ns in the little k is what according to the the mass function of Poisson. That means e to the minus lambda s. Lambda s raised to the power of k divided by k factorial. That is the mass function of the Poisson. So, well, what does it mean when I say I have exactly k arrivals before time s? Let me sketch it again. 0, t1, this is t sub k, fixed time s. This has to be tk plus 1. The length is tau k plus 1. This is tau 1. Let's say tk plus 1. This is tau k. Right? So first, I have the first k gets arriving before time s, and the next one has to be after s. And so this is the same as probability. What can I say? I got it for sure. I know for sure it's the same as capital T sub k is at least s, or is valued from above by s. And what else? I need to make sure the next guy is after s. In other words, I have tk, capital Tk, plus the little tau k plus 1 has to be greater than s. And that will guarantee ns is being k. I have n. I can only have k arrivals before time s. Again, we just have a probability concerning two variables. This could be the first one, and the little tau k plus 1 is the second guy. And so that is just a double integral. Well, the first one, capital Tk is bounded above by s. So that means that is a 0 to, well, I guess before I do that, let me just sketch out the end. Space here, right? Okay. my capital TK. The other guy is tau K plus 1. Alright. Now I know the capital TK is running up to S. And this is the middle S. And then tau K plus 1 is greater than S minus TK. So, alright. This is S here, so the equation here is tau K plus 1 is equal to S minus TK. Yeah. Okay. And I'm looking for tau K plus 1 is above this equation. So that means I'm looking to integrate on this portion of the plane. Yeah. And now that is a double integral. So I'm running from 0 to S. Will allow me to call that to be dx. Alright. F of t sub k. X. Of course, the tk and the tau k plus 1 are independent. So capital TK summation tau I from 1 to k independent with tau k plus 1. Alright. So that will be integral from here to the little x up to infinity f of tau k plus 1 y dy. Okay. Yes.
I have a question. From that equation, would it be possible to just invoke the memoryless property?
The thing is, for the memoryless property, you have a fixed number, a deterministic constant.
Okay.
But here you have a capital TK is a random.
Okay.
So
Alright.
heuristically,
Yeah.
you can say that.
Yeah.
But if you write that in the exam, that's not gonna work. You really have to be rigorous here.
Alright.
Yeah. All right. So let me just stop here and continue on Wednesday.